Okay, welcome everybody. How are you doing? How's it going? Happiness? No? Oh. Anything you can share publicly? Anything we can do to aid in the search for happiness? Okay, it's a rough part of the semester, isn't it? Okay. And this class, as you can see, is got a lot of stuff going on, and I'm grateful that we're getting to do it together. Okay, it's intense. I understand it's intense. Hopefully, though, you'll get to enjoy what's happening, and this is fascinating, actually, because you can't see the screen. Okay, give me 1 second to try to fix this situation. Because we've got multiple things that we're trying to balance here. Okay. Okay, keep these changes. Okay, you can see this. Oh, you can see that. And then we can see this. And then we... Okay, I think that's everyone can see. All right. Okay, so we've got an assignment due this Friday on the initial simulation for your final project. Thank you for your patience. I had a very painful weekend and was able to get you some feedback though. And so if you have questions about the feedback, feel free to send me a message. I'm also behind on the Canvas inbox a little bit, but I'm catching up. Okay. And this demo simulation is a significant, you can see it's worth more points than some of the other assignments have been. So it is a significant step, a significant checkpoint. Nonetheless, we know that we're not needing to demonstrate conversions. Okay, that's going to be the next checkpoint, and that might be a little bit more difficult, right? So this is to try to say, okay, I've got an initial idea, it's kind of working, and we're off, and we know which direction we're going to go. Okay, any questions on this? Okay. And then the next, so of course, there was an assignment due today at 2 p.m., and the next one is going to be due in a little bit on the 8th, so a week from today. Okay? And that will be based on what we covered today, and maybe some of you already started doing lab because that information has been accessible. Okay? Any issues administratively? Any questions? Things you'd like to discuss, ponder, contemplate? Okay. We're looking. Thank you for being here today. All right. I think we will end a little bit early. Okay. And so if you have questions that you want to ask about your project, you can come up and we can talk about it. Okay. So today we're going to discuss how to simulate the airfoils in Ansys, and unlike what I did last year, where I attempted to do the whole thing like in Ansys in front of you, I'm gonna it's really hard to get it right for me. If you look at the assignment, there are like 3 videos, right? There's the importing step, and then there's additional pre-processing, and then there's the simulating, and then there's the whole deal with changing the angles of attack. So I'm gonna give kind of an overview of airfoils, and kind of what we're attempting to do. And I'll refer you to Cillian Thomas and Anthony T. Their videos, and then also kind of I have like 3 videos, 2 that are kind of just for the class, and then 1 course which is out there publicly for everybody. Okay, because I do think that there's some simple tricks that we can play to try to make it easier to go through the angles of attack. But we'll also talk a little bit about boundary layers and kind of how we define both the lift and the drag on an airfoil and the geometry of the airfoils themselves. With the exception, I'm not going to go to like the whole 4-number nomenclature. If you want, you can look that up online, or you can look at airfoiltools.com, which is what we use to get the geometry and bring it into Ansys. We're really focusing on subsonic, okay, all right, today, and we're not going to do supersonic. Okay, so that is not. Let me just. Yeah, this is we're not focusing on that, okay, but we will talk about a range of angles of attack. So when we have an airfoil, we have flow about it, and what have you already simulated that has something with flow about it? We've simulated a wire, right? We've simulated cylinders, or spheres, better. Well, the wire was like a cylinder, but then we simulated spheres in the last homework, in the last session. How are these types of simulations similar or dissimilar to each other? Like, what are the similarities? What are the differences? If I'm thinking about an airfoil, you don't even have to think so much about the simulation, but just think in terms of the real world. How are these simulations, how are these physical experiments similar or different from each other? Yes?
Well, they're going to be different geometries, but you're going to be using the same, in the spherical one, you just use the axisymmetric condition.
Yes.
In something that you need a 3D object, you'll just extrude it.
Okay.
In the cylinder case, you just extruded it.
Okay.
Whereas in the sphere, you use the axisymmetric, but you're going to use the same. Like basically, Ansys is going to do the same thing, like taking the surface integral and applying forces.
Okay, good. Okay, so there are some similarities there, right? You're saying, okay, we're going to calculate forces on the object itself. We've got it immersed, okay, and we can do a 2D planar geometry like we did for the heated wire, which would be a little bit different than the axisymmetric sphere, but it's still a 2D simulation. Okay, so those, yeah, that's fine. What else? When we did the simulation of the sphere, we started where? Where did we start? With what type of flow? Laminar, right? And not even just laminar. We started at the creeping flow, right? And then we moved into the laminar, and then by the end, we moved into this kind of still laminar, right? But if you looked at remember if you looked at the curve, the CD versus the Reynolds number, right? When we got into kind of the final part where it was going from like 10 to 1,000, that was flat. Okay, that was kind of this flat region, and that was still, kind of not super turbulent, but not just like a creeping flow. Okay. One difference might be that typically these airfoils are in high Reynolds number situations. Okay, so we were automatically from the get-go we're running turbulence. Okay, so that would be kind of one thing, and the Reynolds numbers can be much higher. What another, like a similarity though, right? Also, so we were doing things like this. Okay, and right, we had a flow that kind of went like that. I'm exaggerating. Another similarity, right, is that, well, right, it's hard for you to read my mind. Okay. And reality, this is going to be different. Okay. Yeah, we would have, flow that's kind of like this, right? And as we get farther away, right, essentially you have these streamlines. What is mine not good? My drawing really bad. It's okay. You can make fun of it. That's okay, right? So you know that the far away you have flow that's more or less uninterrupted. Okay, and we did some work in terms of trying to describe the geometric necessity for convergence. One thing that will be different is that in the airfoil, we actually use a much larger domain. 7.5 times one direction, 15 times in the other direction, right? Whereas when we were doing our flow about sphere, we were pretty much using a pretty small domain. Okay, so that's maybe another difference. Another difference is that in the case of the sphere, we were only interested in one direction of the force. Okay, that was just the drag. Now, yes, you could superpose, you can have, but there's really no orthogonal component to it, okay? And yes, we can think of lift and drag as one superposed force, okay, as a composite. Nonetheless, when we do airfoils, we're going to be considering, right, the lift. Whoops. Okay. So we could call that FL if we want, and we'll also be considering the drag. So those are maybe some other differences. Now, the applications, of studying both of these objects might vary a little bit. Can you think of applications that are interesting for studying the flow about spheres? Like, when would you want to think about lift and drag on a sphere? Sure. Right, so lots of balls, right? So there are a lot of things where you throw projectiles or balls, right? That's a good time to figure out the lift and drag. Actually, just usually, well, if it's not spinning or if it doesn't have some interesting geometries on it, right? Like when we did the bouncing ball, we were just concerned with drag in one direction. Or in the opposite direction of motion, better said, right? That's the vector. It could change, but now, when you have the spin or you have different things, yeah, the balls could be rotating and could have dimples on them or something, and it could have a force that's going not just in line with the direction of travel, right, but a little bit off from that. Okay. So that might be one application where you care about lift and drag, or drag on a sphere. Okay, balls. You could sometimes you seed, and this is a little bit different, where you seed particles that are spherical into devices to capture flow, and that, how it moves with it. In those cases, usually you hope that the balls or the beads or the particles that you're using to image the velocity of the profile, that they're just going along with the flow. Airfoils, you can think, wow, okay, planes, flight. You can think hydrodynamics as well. Has anyone used, anyone done any foiling on water? I haven't. Are you familiar with this? Right, where you have, well, anyone seen these, like, you know, it started off with, well, let's see, where did it start off? I don't know. It's now both recreation and professional, right? So like the kind of sailing, World Cup sailing, right? They used to just have the holes and everything, right? And there you go. Now it's like these systems where they get propped up on the foil, right? And there's a significant decrease in the drag, okay? Because the overall surface area that's on the water is much less because these foils generate enough lift. Okay, so that's been one place in hydrodynamics that this has occurred, and you can argue that both planes and hydrofoiling are going to be affecting transportation. Some of you are interested in doing the modeling of turbines for your turbines for your projects. That's a little bit tricky because you've got foils that are going to be experiencing different velocities through the air as they spin. Nonetheless, you know, you can make some approximations for how that foil will behave. So those are some of the other applications. And we talk about surfing a little bit, right? You now know me a little bit, right? So a surfboard exhibits a lot of the properties of a foil as well. And we can talk about them in terms of how you might look at the drag coefficient, how you might look at the chord length, how you might look at the span. And you can also think about what happens at different velocities. So when you're paddling on the surfboard under your own power, you're not able to generate enough relative speed between you and the water, or the board and the water. And so you're kind of just plowing through the water. Okay, and they call that pole speed, H-U-L-L. Okay? But what happens is magical. Well, I guess it's physics, it's not really magical. When you start to catch that wave, there's enough water and enough gravity that the relative velocity goes way up. And you jump into a planing situation, all right, where the drag is significantly less, just like a hydrofoil or something of that nature, where you decrease your contact with the water and you're able to progress with much less drag. Okay? So those are some of the applications of foils. Some of you want to do supersonic modeling for your final project. That's okay, except I suggest that you stick to very simple geometries like a wedge or something, because well, one, we're not going to cover supersonic flight in examples that we do, and two, they're much more complicated and you have shock waves and those effects. Okay, so another interesting thing that happens with foils is separation. And in order to understand separation, and this is not like, you're separating from your family or anything like that. This is separation in the flow, okay? And to start, you're taking fluid mechanics, you're taking some fluid mechanics now, right? I asked the other class, and maybe in the last week, have you got to the boundary layer problems yet? No. Glossius? No. Boundary layer? Okay. So here's a little fluid mechanics for you. This is a lot of fluid mechanics today, right? I put a plate, flat plate, like you see here. Flat plate. And a lot of times they almost like put a little knife edge or something there, but it's just a flat plate. And I start running air over it. Okay. That plate can have some drag on it, right? You could even though it might have a very small front cross-sectional area, it has length, and there can be shear, right, along here that exhibits some drag. And I still have the no-slip boundary condition. Okay, so what does that mean? That means at distances that are very close, okay, to this plate, I have zero velocity, okay, because that plate's not moving. Or you could say, I'm going to spin a plate, or I'm going to move a plate through the air, right? The air is fixed, whichever. Okay? You can see that this is analogous to an airfoil in some respects, right? I've got flow coming over a plate, and I'm interested in what the fluid mechanic behavior is. Well, if I'm right here at the edge, like close to the edge, turns out that some of those fluid particles are like, oh, I'm stuck. So then as I go a little bit further from the edge, it's like, oh, I'm holding back, right? And as you progress along, you see that you get a profile, and it's kind of parabolic, right? So at this point you've done pipe flow, right? In fluids. Yes, right? And so you solve for the boundary conditions, right? You have zero velocity, right? And you create the parabola, or the paraboloid, or so, okay, right? So this is just like 1/2 of that, okay, without the other. What's interesting is that this kind of layer, okay, separating arguably something that's close to free stream and the innards, all right? So when this velocity, see how this velocity, if you're talking at this location, the velocity it starts to become essentially flat, right? So whenever you draw these lines, it's confusing in fluid mechanics, right? But we're looking at the velocity along this vertical line, but then these are the magnitudes, right? So you see that after you get outside of a particular distance, delta, essentially the velocity doesn't change that much. You can see that? And this boundary layer keeps growing. Okay? And there are equations that tell you how to calculate it. It also is interesting in that the Reynolds number changes as you get further along. So we define a Reynolds number as a function of x. So here x is equal to 0, so the Reynolds number is very close to 0. Right? And you can see that the velocity right above it hasn't changed much from the free stream velocity. But as you get further along, the boundary layer grows and the Reynolds number grows. And what happens? Well, you get this kind of boundary layer that defines a bunch of quasi-static fluid. All right? Or it's got it's not quasi-static, it's actually just the opposite. All right? But just think with me, right? And it's kind of like, wait, but the stuff out here wants to go at a certain velocity, but the stuff here is all like held back, and there's a distance, and it's just gas, it's just air, whatever it is, and it becomes unstable. And it starts to create eddies. That's turbulence. Okay? So you get a fluid flow where it's laminar, close to the edge, the starting point, and then it becomes turbulent as you get further away. This happens with airfoils as well. At some point, you're going to get separation. Right? So you can think, oh, there's some kind of boundary layer that's forming, and it's going to separate and become turbulent. This leads to general inefficiency. Right? Now you've got all this air that's swirling around and stuff. The ideal airfoil, if possible, if it existed, would be something that would be nice and laminar. You get nice reconnection. Okay? But that's not theoretically, well, maybe theoretically it's possible, but practically it doesn't happen. Okay? So there's a couple of things to take away. One is we have relationships based on dimensionless number, Reynolds number, as a function of x, and of course the density, velocity, and this is free stream velocity, and the viscosity. We can determine, okay, how does this boundary layers forming, and there are different relationships that you might find. And then this transition from laminar to turbulent flow happens at 10 to the 6. Now, you can watch different YouTube videos or read different papers and the Dallenberg paradox about why things really fly. Okay? The rough approximation we're going to go by here is that, well, what does everyone usually say? Like, what is the one sentence version of why airfoils work, why they generate lift? Yes.
Is it because there's a higher pressure below the foil than above it, so kind of pushes it up?
Yes, okay, and then can you just add maybe a conjunction like and, because, or something? Why is that? Also in that one sentence.
Because of the design of it?
That's too vague, that's too vague. Go to the physics a little bit, right? So you're right. Airfoils generate lift because there is high pressure below the airfoil and lower pressure above the airfoil. That's true. So let's see how we can make it one sentence without making it two. We could say the lift force due to high pressure below and low pressure above occurs because come on, yes.
The speed of the air is different on the top and the bottom.
Yes, and low pressure is associated with
Low velocity. High velocity.
yes, yes, yes. Okay, right? We're mechanical and aerospace engineers. Okay. Yes, right? Okay, so remember that thing called Bernoulli's law? Okay. So this is not like people will say there are paradoxes, there's shear, there's turbulence, there's all kinds of stuff, right? But like the basic idea is this, right? That you have high velocity on the top and low velocity on the bottom, which means that the pressure on the bottom has to be high and the pressure on the top has to be low. All right? And if you're a car person and you have a spoiler, you're doing the opposite. You just put the airfoil upside down so that you have high pressure above and low pressure below. Now, why did I say Bernoulli's? Because remember, Bernoulli's is something like does this look familiar? I think I wrote it right. Okay, so, right, the V1 is at one location, okay, and the V2, or the H2, the P2, right, they're at a different location. Okay? And we have conservation, essentially, of energy and momentum, and all these things going on. Okay? So, if I have a spot, right, where I have high pressure, I've got to have low velocity if it's going to be compared to a spot where they have low pressure and high velocity. You see that? Okay, so this is kind of like almost a hand-waving first order approximation to why there's lift. Yes?
One of my classmates say that it's because the air is going faster over the top of the foil than on the bottom. Is that what it is?
The air is, in fact, going faster, okay, on top of the airfoil, which means there's low pressure on top of the airfoil.
It's not the other way around.
It is not the other way around, okay? And so we have this beautiful little demonstration, okay? And someone asked, how did they do this simulation? I'm not exactly sure what they did, but let's just follow the profile, okay? Dot, 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 dot. Okay? It's all And what happens?
It disrupts the top flow.
Right, and how is the flow above? If this were a car race, and these are all the little cars, who's winning? The arrow on the top is winning. And sometimes, like they say, oh, it's because of that camber on top, the air has to travel a greater distance in the same amount of time. So therefore, the local velocity has to be higher than the velocity that's like just below it, then below the airfoil. Okay? So, yes, go ahead.
Maybe I'm just being too picky, but like, there's not more friction on the top because it like, there is, I don't know.
Well, so yeah, so there's a larger area, and yes, you could say so. Like, this is the first order. Like, when I say first order, this is like the kind of elementary reason, right? But people, fluid mechanicians, a lot of people have there are paradoxes. There are all kinds of things about, like, you just Google YouTube video, like look at Veritasium, they'll say this is why the foil really works, all right? Because we're like, no, it's really this, it's really, yeah, okay. I mean, you also have turbulence involved. You also have the eddies. You have a whole bunch of things that are happening. This is kind of like the easiest way to understand, and not completely like sound physics. But this is more or less true, right? So like we're going to be simulating airfoil, so it's a good idea to know just a little bit about the overview of how these things work, right? So that we know, like, okay, this is what our fluid simulation is telling us. And I hope you'll agree that this equation is in agreement here with what we're seeing here. Okay? So we've established, and it's a little funny because you're like, oh wait, this is actually losing the race. No, this is almost catching up to the next one. You see, as it comes around, right? This one is speeding up over the foil, and it's almost going to catch. It's almost lapping, for lack of a better word, its neighbors on the other side. Okay. Any other comments? Okay. So there are a number of things that affect how much lift you're going to have, and things that affect the drag as well. And then people often look at the ratio between these two. They look at the lift to drag ratio. Okay. What are some things that I can do, you think, to affect lift and drag here? Yes?
Increase the cord length.
Right, so it can increase the cord length, right? Now it turns out that we're going to use dimensionless numbers, right? CD and CL, the coefficients of lift and drag, right? So that it won't, dimensionless world, right? It's not going to change things. But yeah, absolutely. You change the cord length, you change the span, you can get more lift and drag. But the ratio between the lift and drag is not going to change. Okay? So that's a good point. What's another thing you can do? Yes, Rishi.
Could you increase how thick it was so that the height term it matters? Like,
Yeah. Yeah, so in fact, that's what you'll see. And if you look at the airfoil tools, or you just look at the nomenclature that we use to name, you'll see that as you increase the numbers, some of the numbers, you'll see that you can make it fatter, okay? And when do you think you want kind of like a thicker foil? Often lower speeds, okay? Right? Now another thing you could do is you could try to make it symmetric. Now what happens if you make the airfoil symmetric? Like the top and the bottom are the same as that camber. Do you get any lift out of that? No, you don't. So what do you have to do in that case to get lift? Can I fly? Yes, go ahead. Yeah, so you have to change the angle of attack there, right? So you can have a symmetric airfoil, and then essentially you just like you do on the little paper airplane thing that you have, right? You can get it, you can fire it off. Oh no, this always scares me. Please don't do that. Please. Yes. Okay. That's weird because these screens didn't go blank, but this went blank. So like there's this. So yeah, that's another thing you can do, right? Another thing you can do is you can change the camber. So you can do things like this, okay? That will affect the lift to drag ratio. When you take off, and you can do this in real time. How do you do it in real time? Use flaps. All right. So have you ever looked out the window and seen what's going on when you're taking off or landing? All right, when you're going in for landing, what do they do? They bring the flaps down, right? Why? Well, because that gives you more lift, it gives you more drag, but it allows you to have enough lift at lower speeds so that you can land. Okay? So these are all things that you can play with, and people have played with in their designs and with their wind tunnels. Even the Wright brothers, they had a wind tunnel. They made a wind tunnel, and they were testing things out. So, let's talk about some of the metrics. And these are both geometric quantities and also the coefficient of lift, the drag, and the parameters that we measure when we're doing the experiments, the forces. Okay. So again, I'm not going into like the 20% this, the 40% that, because we're going to be studying in 2412. Okay. But the basic kind of thing is that, as people said, we need a chord length, which is how long the airfoil is, and we need a span. That's how wide the airfoil is. And in 2D, which is what we do our simulations for this lab, it's the dimension, or we're only using 2 dimensions when we do simulations in the lab. We essentially just say that the span is 1 meter. And that's a pretty good assumption. A lot of the 2D, like you're like, how do I get this 3D number? Like, I got to get a force out of it. It gives me force, but like, in order to have a force, I got to have a depth. So usually the simulation software say 1 meter is what you're going to use. The area, this confuses me, and you're very smart, so you won't get confused too much. I often think, because my PhD was in spheres and in liquid bubbles, right? So I'm just like, I need the cross-sectional area, and that's like kind of this frontal area that's hitting the liquid, and that's going to be my my area that I'm caring about. Okay, when I because I have this. Do I have it here? Yeah. So like the force, right, is going to be like 1/2 rho v squared a times some type of coefficient, CD often, right? So the A I think of as this frontal area. But in a sphere, that frontal area is also the same as the circumference if I look down on it. Okay, I mean not the circumference. It's the area if I look down on it, right? Here, that's kind of more the definition we're using. And that's partially for, one practical reason so we can compare. So if you define your airflows, like it's going to be hard to come up with a frontal area, okay? Or like if I'm looking at the airfoil, it's going to be hard to have like a frontal area that's like kind of telling the same story. But if I have B and C, and yeah, I have like these different thicknesses and profiles as I go along, that B and C is pretty much uniform through it. And I think I've confused my senior design teams when we've talked about, I know I have, when we've talked about lift and drag, well not lift so much, more like drag on a surfboard, because really on a surfboard you also have, like I said at the beginning, a chord length and a span. Okay, so we do some stuff with surfboards, trying to do propulsion on them, and it's the same exact kind of quantity we can use. Okay. Now, this is just my scribbling from last class, just to say, okay, yeah, CD and CO are in fact dimensionless quantities, okay? And you've already got some experience using this definition of drag. When we were talking about creeping flow, if you look at the about a sphere last time, right? We said it was 24 of the Reynolds number was the force. No, or was the 24 of the Reynolds number was the drag coefficient. Sorry. Okay, and we could use that to calculate the force. That was a little bit weird. right? And then you got to certain regimes where like it was more, you entered the drag crisis at some point, but it was more or less flat in these more turbulent, high Reynolds numbers regimes. Okay? So we are using Ansys to calculate the forces with the given geometry, and then using the V, the A, the rho, okay, to be able to, and D and L, those are forces, right? In this case, those are not lengths; those are actual forces to calculate these coefficients. And there are ways to do it in Ansys. I talk about it in the videos a little bit, where you can go into the references and you can set the reference for the rho, the reference for the velocity, and then it will calculate your CVs accurately for you. Or what we also do in the videos and in the lab is to say, oh, I just want the force. Just give me the force, and then I'll go in MATLAB and I'll calculate the CV and the CL. Okay. Any questions on this? How this works? So you're gonna be doing this for the lab for sure, and it's just, I think it's a good idea to have a rough idea of what's going on here. Now, I gave away my answer. Okay, you didn't see that. Okay, and you didn't see that either. Okay, so alpha here, what is alpha? Some of you said it already. Angle of attack, right? So then that top one is angle of attack equals 0. What do we see? When we calculate lift and drag, the drag component is always parallel to the free stream velocity. Okay. And that you can say, oh, that makes kind of sense. Well, why does it make sense? Well, one, we vary the angle of attack, you know, that what does that mean? That means that on a plane, the plane itself, right, is still going against, you know, the plane can change its angle of attack, but we're still interested in, okay, what is the lift relative to the velocity of the plane, right? I mean, we are interested in the angle of attack as well, right? But so the free stream velocity, okay, is going to be orthogonal to the lift, okay, and parallel to the drag, all right? Now, if you were designing an experiment, now, okay, so we're going to talk about the differences between manipulating angle of attack in simulation and experiment. If you're designing an experiment, how would you manipulate angle of attack? You got a wind tunnel, yes.
If your wind tunnel is advanced enough where you could change the direction of the flow, then you would do that. If you have a 4-man wind tunnel, then you just keep the flow in a certain direction and change the angle of attack there.
Yeah, I agree, right? It's a lot easier. You got this little airfoil, right? And you have this big turbine or the big wind tunnel, right? Do you want to like keep the foil fixed and like I want to change I mean, I'm sure some people do it this way. Okay, change the whole wind tunnel. No, right? You're going to want to keep the wind tunnel probably, you know, horizontal, and then you're going to go in and you're going to change the angle of attack on the floor. Okay. Now, why would you do it differently in simulation? And first of all, what am I saying in simulation? What am I doing in simulation? There are people that do change the angle of attack in simulation. Okay? I'll argue that's not the best approaches. So, okay. What do you have to do in simulation? You have to put the geometry in, right? And can you change the could you move the airfoil geometrically? Sure, you could do that. Right, that's not that hard. What comes after, what's the next step in your pre-processing though, before you run the simulation? The mesh. And what have we learned about meshing so far? All right. It's an art and it's variable and things don't always converge, right? I mean, maybe a few of us were able to get the meshing and everything. Oh, actually, you haven't done this right. A few of us might be able to get the meshing and everything to converge on this this lab the first time. But I'm going to guess that a lot of us are going to have to do it multiple times just to get the mesh right, because it's an absolute pain. So let's say I've got my mesh beautiful, or I've got my mesh all set up, and it's converging, and I've got a simulation at 0 degrees angle of attack. Do you think I want to rotate my foil and then have to remesh the whole thing again? No way. Okay. So what instead we do is what you see here. We change the direction that air is flowing against the foil. Okay. And we use a domain that is, well, I kind of drew it up here a little bit ago. Kind of like this, like a C shape, all right, like the letter C. And we are able to essentially, oops. Oh, okay, well, here you go. It essentially looks like this, and we can bring in a velocity, like say this way, right, where it's all the way like this. You can even prescribe velocity on these sides that are inlets, right? And they should be all the same vector length, and that's 0 angle of attack. Or you can get to angle of attack of like 10 degrees. I don't know if that's 10 or not. Okay, like this. I'm like trying to be non-committal to my, that is not 10 degrees. Okay, anyway, but you get the point, is that you can bring in the velocity at different angles. Now, how does Ansys calculate force and drag load? It's calculating it like that. Ansys is telling us, and most softwares are going to tell you what it is relative to the coordinate system, not relative to the airflow. Right? Because lift and drag, as we discussed, that's when you look at what's happening with an airplane, right? You want to figure out what the component of lift is orthogonal, perpendicular to the flow coming in. Right? So what do we have to do? We use more circle. Just kidding. Just kidding. Trying to wake you up. All right? No, you don't use more circle, but you just use a free body diagram. Okay? And here it is. Okay? No, that's not it. There it is. Okay? So you see that fluent, we'll call L fluent and D fluent. Okay? They are linked to the coordinate system. And we're specifying the velocities. We're actually breaking the velocities into an x coordinate and a y coordinate, right? Based on the angle of attack. And so we can do that with cosine and sine. That's really easy. Okay, so yeah, we'll bring in those velocity components as we change the angle of attack. But we need to think about how to define the vectors that are going to be parallel or orthogonal to the direction of the flow. So in this case, if I want the true lift force, okay, and Fluent is telling me it's this, what do I need to do? I need to decompose, or I need to construct, right, sides of a triangle that when I add them to each other, I get this vertical component. And the same thing for the drag. I need to construct sides of this triangle, this right triangle, that will give me the drag component. So this is how you calculate the lift and the drag. Parallel, the lift orthogonal to the flow, and the drag parallel to the flow. It's pretty simple, okay? And you want to do this in MATLAB, okay? Yes?
Can't we just, like, I understand, but can we just use Ansys and when we define force of drag, can we just put in the vector that is with the
So my experience, no. You might be able to do it, but I couldn't put in a non-1 or 0 when I tried to do it. Okay, when you define the vector. You're absolutely right. Okay? You ought to be able to do that. Okay, because it's not that complicated. Maybe there's a way to do it, but I didn't figure it out. So you'll do this in MATLAB. You can look at the video to see how to run that code. Okay. Now, when we talk about convergence, there are a couple ways to do it. In this lab, you're not going to look at convergence as you change the mesh and stuff. It's too complicated. Okay, well, or I don't know. It's not. We're not doing it that way. Here, what we're going to use for convergence is the ground truth. And where do we find the ground truth? From experiments. Where do we find these experimental results? In the nice little wind tunnel. We're not taking you to a wind tunnel. We do have wind tunnels in measurement in senior labs. You'll use a wind tunnel. Okay. But what instead we can do is we can look at the literature. Okay. And so an example of looking at the literature is here. This is a paper from 1977. Okay? And it's beautiful in its simplicity. They could do all these calculations without computers, as manifest by the beautiful plot that we're seeing here. Okay? So this component, or this direction, is lift, and this here is degrees of angle of attack. And we are going to be looking at simulations with a Reynolds number of about 2.2 million and, and clean. Ooh, clean. All right, that doesn't like that much. Okay, the clean one. Okay. They have some experiments from another paper, I guess at 3 million, and that's pretty good. I mean, if you do something in one lab and then another lab does it, or you do it on another day, right, and you're the same order of magnitude in your Reynolds number, and the curves follow each other like this, you're happy. You publish it, right? And that's what they did. And then they were also looking at having grit involved. So like putting sandpaper surface on it. So what we can see here, the clean are the squares. So where are the squares? The squares are like kind of in the middle. There's a square there, there's a square there, and you can kind of see, okay, for this Reynolds number, I can see at 4 degrees, I had, and actually all of them are remarkably similar. But I had a coefficient of lift of 0.6. Why do you think they care about like 0.6, 0.55, 0.54, 0.5? Why do you think they care so much?
You can use it on an airplane that's like, I don't know, 100 feet long, and that makes it.
Sure, that's one. What if you care about fuel efficiency? If I'm telling you that like I can increase my lift to drag ratio by 5%, that's a big deal, right? And some of the things that they're trying to do now with different prop designs or different things on the thrust end, they're trying to increase their fuel efficiency quite a bit. Okay, so this plot over here is now a CD versus CL. So what you have to do if you're running your angles of attack at 2.2 million Reynolds number, then you're going to be looking at what's your CL first, and then you can come over here and you can write and you can see what your CD would be. So if my CL was, this is 2, 4, 6, 8, 1, right? So let's say we're at 0.4, then you could say, oh, my coefficient of drag is, this is 0.01, 0.02, 0.03, 0.04. This is going to be, it's like 0.07. I'm sorry, 0.007. Something like that, at 0.4. See that? Right, because this is 0.01, so it's going to be like 0.00 something, less than that. All right? And so when I ran my simulations, and I mean, Anthony T and Cillian Thomas and Anthony T also ran their simulations. Okay, and then I ran using their methodology, and then I used my way of calculating lift and drags, or not my way, a way to calculate lift and drags. You can see that the agreement was amazing. I was like, whoa, this is incredible. Okay, now the coefficient of drag is off. Okay, it's like 30% off, but I'll take that. Okay, I'll take that. And so this is kind of what your lab is going to be about. Any questions? So it's pretty involved. You'll see you spend a lot of time on the pre-processing, and then I guess you probably have to think a little bit about the post-processing. But I think the meshing, the getting the geometry is actually remarkably painful, unfortunately. And while you're slugging away at it, you can just think, all right, I'm building skills for the future. All right. So I don't know. It's pretty tricky to get this to work. All right. Any questions about what we discussed? All right. So we'll go ahead and do the attendance, and we'll end a little early with the lecture portion. If you have questions about your projects or whatever you're doing, I'll hang around for another 20 minutes to chat it up with you. Okay.